Hello everyone, my name is Peyton, my lab partner is Kaylee, and today we will be presenting on Vraylar synthesis.
The information being presented can be split into 5 sections. We will present some background information on Vraylar, a reaction scheme and mechanism of the drug synthesis, the scope of the methods used, and general applications and limitations of the reaction scheme.
So what is Vraylar? Vraylar is a prescription medication used to treat major depressive disorder and schizophrenia. The drug is considered an atypical antipsychotic, which means it tends to have fewer and less severe side effects than first-generation antipsychotic drugs. In its structure, Vraylar has a piperazine ring, which is a saturated ring with 2 nitrogen atoms that has important pharmacological properties. This drug was first developed by Gideon Richter and Forest Laboratories in 2015, and the generic name of the drug is cariprazine. Vraylar helps restore the balance of chemicals in the brain to help improve a person's mindset of themselves and others. This drug shows potential in being able to treat schizophrenia and certain forms of bipolar disorder.
We have found at least 10 different reaction schemes that can be used to synthesize cariprazine. Some examples of reaction processes that were used include Wittig-Horner, reduction of alkene, hydrolysis of ester, diacylation, and more. The reaction scheme that we chose to focus on was developed by Gideon Richter and Forest Laboratories and serves as the original synthetic route for cariprazine. The scheme involves 5 main reaction processes. This slide displays the entire reaction scheme for the synthesis of cariprazine. The first reaction is a Buchwald-Hartwig reaction. This is done using compounds 1 and 2 as shown above. This reaction was refluxed for 8 hours to produce compound 3. The second reaction is the Bach deprotection of compound 3. This required the use of gaseous hydrochloric acid and ethyl acetate. The third reaction is the reductive amination of compound 4 with compound 5, which is above the reaction arrow, to yield compound 6. The fourth reaction is another Bach deprotection to produce compound 7. The last step of this reaction involves reacting together compound 7 and 8 to produce compound 9, which takes a total of 48 hours. This involves a follow-up treatment using dimethylamine and diphosgene lasting for 20 hours.
The first step starts with the lone pair on the amine attacking the bromochloride benzene ring and kicking out the bromine and replacing it. And then the next part is the bromine ion comes in and deprotonates the amine to make it neutral again. The oxygen in the Bach protecting group grabs a hydrogen from the hydrochloric acid in solution to become protonated. Once protonated, the tert-butyl group folds down its electrons to make an alcohol. Then the negatively charged chloride ion comes back in to deprotonate the alcohol, and what remains of the Bach protecting group leaves as carbon dioxide as the amine gains a hydrogen.
This reaction starts with a negatively charged boron of the reducing agent attacking the carbonyl portion of the aldehyde. This results in electrons being pushed up to the oxygen. The negatively charged oxygen is then able to protonate itself using a proton from DCM to form an alcohol. The oxygen protonated itself again using a proton from the amine produced from the previous reaction process. The negatively charged nitrogen then attacks and pushes off water.
This step shows another Bach group deprotection. So again, the lone pair on the oxygen grabs a hydrogen from the hydrochloric acid. The tert-butyl group then folds down to make an alcohol. And again, the alcohol is deprotonated by the negative chloride ion, but this time when the carbon dioxide group leaves, you're left with a primary amine.
This reaction starts with triethylamine removing a proton from the amine. The negatively charged nitrogen atom then attacks at the carbonyl portion of the dimethyl carbamyl chloride. The electrons of the double bond are then pushed up to the oxygen, then back down to remove chlorine.
Key features in Vraylar synthesis is the presence of the Bach protecting group, of which can be seen in the image to the right. The use of this protecting group is done twice in Vraylar synthesis, and it helps protect the amines from hydrolysis. In other kinds of reactions, such as peptide synthesis, Bach protecting groups can be used on amino acids to prevent polymerization and other side reactions from occurring. In order to remove the protecting group for other synthetic steps, simple carbamate hydrolysis and acidic conditions can be done.
Some key reaction processes from this reaction scheme include the Buchwald-Hartwig reaction and reductive amination. The Buchwald-Hartwig reaction involves palladium-catalyzed synthesis of carbon-nitrogen bonds. This reaction is generally used to cross-couple amines with aryl halides. Reductive amination is the synthesis of amines from aldehydes or ketones. This process is commonly used to synthesize secondary or tertiary amines. The reaction scheme that was selected was the first synthetic route for cariprazine. Therefore, there are many things that can be improved. One of the biggest limitations that we noticed was the long reaction times, ranging from 8 hours to 48 hours. Ideally, the reaction time should be much shorter, especially if mass-producing a drug like Vraylar.
Thanks for listening.